So this presentation is about how to design anything, or at least start designing anything. And this is what we're going to be chatting about. So specifically, we're going to talk about the beginning part of the design process. So sort of from that first step of, I have a blank piece of paper and we need to make a car, up through sort of the point where you have like a really well-defined picture of what the system could look like, as well as like the things that the system needs to be able to do. Things we won't be covering this week: we won't get into analysis. This won't be a lecture on ANSYS. We won't talk about bulk calculations. That stuff's not this week. We are planning on covering it in the future. And so if you're interested in that, tune in next week. And then these are sort of the big sections of the presentation. Essentially, what are requirements anyway? How to set good requirements. We're going to design a desk lamp, which is going to be fun. And then we're going to talk a little bit about how that process applies to Mark V. All right, so it's really easy when you see systems like this to just like get overwhelmed by the complexity, like of a formula car, a rocket engine, even something that's like appears somewhat simpler like a phone, or even just like a simple desk lamp. Like these things are all extremely complex systems. So it's really hard to imagine designing or even like coming up with from scratch as a student engineer. But speaking from experience, sometimes you'll show up to your summer internship and they'll be like, here, design this whole thing. You have 7 weeks. I don't care how much it costs, just do whatever. And so you need to be ready to deal with that. And so in my case, it looked exactly like this. There's literally a blank piece of paper on my desk, and they were like, oh, make this thermal chamber for these satellites. And I was like, I know nothing about any of that. And so the classic question always gets asked, how do I get started? And the answer that is very consistent is that you need to figure out what the thing that you're designing needs to do, which sounds really dumb, but that's sort of really hard to get all the way down to the essence of, because like function is much more complex than just like, oh, it's a car, it needs to drive. Like, well, how does it need to drive? How fast? Like, in what ways does it need to handle? Things like that. But a really interesting example of function is that this like highly tuned race car, which is really, really good at being a race car, can't do something that your simple desk lamp can do really well, which is light up your desk. And so even though these two designs are like vastly different in complexity, vastly different in cost, vastly different in effort, they're both successful because they've fulfilled their goals, and they've fulfilled the functions that were originally set out by the design team and designed to. And something that's really interesting is in the natural world, you see something called convergent evolution, which is like where there's a certain problem, like for instance, bats not being able to see at night, dolphins not being able to see clearly underwater. And there's a common solution amongst all sorts of different species. Like they obviously didn't learn it from each other. And so there's a common solution to the same functionality that's required. And that's really interesting because that means that there's sort of like an optimum and there's like a place, a direction that all designs trend towards. And you can also see that like all these different varied creatures like have sort of turned into the same shape when that function is moving efficiently in water. And so then back to the formula example, here we have two teams. They're probably not sharing IP with each other, so they don't know anything that the other team knows, but their cars are almost identical. And as long as you ignore the abstraction of rules for the second, you'll see that they have that their designs have converged primarily because of the functions that they're trying to perform. And so both things are trying to go extremely fast, they're trying to produce a lot of downforce, trying to carry a human, all these things. But they look extremely similar, but they obviously function somewhat differently, because here you see the Mercedes car finished first in 2019, whereas Renault finished sixth. And so then it sort of evolves from like this initial understanding of like, oh, it's a good design versus it's a bad design, into like a scale, right? And so in this case, like if your function is hammering nails, your toothpick is really bad at it, but a hammer is really great at it. And there's actually kind of like a continuous range in between of things that are like okay at functions they weren't designed for, or were maybe designed improperly. And so what that gets to is the idea that choosing design requirements is the most important aspect of design. Like if you were this Renault engineering team and you like decided that, oh, it was really important for the car to be shaped like a hot dog, Like that might not fulfill the role of it being a great race car. And so it would look a lot more like a hot dog, but it wouldn't drive as well. And so if you set your requirements wrong, then your final product is not going to act the way you want it to.
This is why Alex is going to SpaceX. Lots of hot dog designs.
Yeah. Also, I pity you if you're in Mech Solids and didn't get the hot dog example.
Pressure vessel.
Okay, so then the tricky part of that is like you've seen all these examples of poorly defined requirements, poorly defined functionality. So how exactly do you define that? And the answer is something called requirements, which are essentially like a list of tasks that your system or your component need to be able to do in order to be successful. And the idea with this is that if it fulfills all of those tasks, then it will be a successful design. And so it gives you both a list of things to work towards and a checklist to complete at the end of design cycle. And it's really easy to look at something like a car and be like, oh, look, this was well designed to win. But it's really hard to go from a blank piece of paper to that complete car because there's so many options. The solution space is so huge. And so hopefully we're going to talk about is how to take that huge space and figure out what exactly you can design for. So we're going to walk through a little bit here. We're going to try and think of what we need to do to design the optimum desk lamp. And something that's really tempting to do that I've personally done a lot is if you're given a task like this, you just need to be like, okay, so it's a desk lamp, right? Like it needs to work and it needs to not break. And that's all it needs to do. Just 100% functionality, right? And that is not a good way to think about it because you have these sort of ambiguous, vague goals and you really want to break them down into concrete statements of function. So I took the liberty of doing that for this desk lamp. Essentially what it needs to be able to do is it needs to be able to light up space, plug into the wall, and be ergonomic in some sense that like a person can interact with it, they know how to turn it on, pick it up, move it, whatever. And so these are also not great requirements because if you look over here, you can see. I know. Thank you. Sorry, I was pointing with my finger on the shadow of the projector for those of you that aren't in this room. But essentially, you also want to think of these things as being as descriptive as possible. And so saying something sort of vague, like, oh, I want this car to be as fast as possible. I want this part to be as light as possible, as cheap as possible. That's really poorly worded because it doesn't give you like a specific objective and you have no idea if you actually hit it. And so you should replace those things with like very specific metrics like, oh, our car needs to be able to go this many meters per second, needs to weigh this many kilograms and cost this much money. And so you can't leave it up, or you can't leave with just like these fundamental requirements. You have to have like more, you have to put more thought into it and come up with derived requirements, which actually have like specific numbers and specific metrics that you can measure on your final design to determine whether or not it has succeeded. And this slide I skipped is just that context is important because like these foundational requirements are really good at defining the technical solution space, but sort of like the soft design aspects that Olin is so good at teaching you are really important to also remember. So like thinking about context, especially, or like partially for the desk lamp, but especially for like the larger, more complex projects you get into in your careers is very important. And so here, I'm not going to go into depth into how I went from this fundamental requirement to the derived requirement here. I will at the end of this presentation, but essentially this is where most of the engineering work happens before you actually get to the point of analysis. Because defining what is meant by lighting up a space is very difficult. Or like plugging into the wall, like, well, okay, are you using like 50 hertz, 60 hertz, 240 volts? Like, are you living in a trailer? Do you have solar panels? Like, it's just it's a very large solution space. And there's a lot of work that goes into buying it down. And so then I've taken these requirements and I've plopped onto this slide. And what's really useful about requirements is that they allow you to think about problems more creatively and sort of have things to latch onto. And so if your problem is that you don't know how to get started on something, this sort of gives you a list of tasks that you can do to get to the point where you're confident that your design will be able to complete the functionality. And so like I just sort of went through these and like came up with a couple ideas. And they're really helpful to be framed as questions because that allows you to answer them in all sorts of ways. And so like these are all totally functional desk lamps that fulfill the requirements.
Well,
But see, that's the interesting thing is that you didn't set a requirement for what it needed to do or like what sort of environment it was going to be in. And so like your 3D Shrek lamp could be perfect if you want to just like hang out and chill at your desk. Whereas the duck lamp could be really good if you want to write. That was, I actually found that one in an article of like 5 items every writer needs to own.
a duck lamp.
Yes. But the point is, these requirements, give you something your design has to be able to do, but also give you unique insights into the avenues that your design could pursue. And so like 100 lumens of light could be 100 candles. It could be a spotlight really far away or a bucket of burning magnesium chunks. Like there's a lot of creativity that comes with that. And so like once you get to that point, you have your requirements, you have like this very specific list of numbers that your design needs to hit. The next step that I'm not going to go super in depth in is sort of that ideate, come up with a bunch of different ideas that are super creative and out of the box, do some sort of like gut check, like is this actually feasible, decide on a direction, refine it, do a bunch of analysis, and be confident that your thing is actually going to work. I'm going to switch a little bit to a different section of the presentation. If you guys have any comments, questions, want to just see these lamps again, let me know. And
Yeah, let's pause for a second.
yeah.
Do you want some water?
I also looked up weird desk lamps to get these pictures.
Alright, so he went to his own desk.
Are you gonna go into
What was
the gut feel part of this?
Not today, but that is going to be a presentation in the future where we talk about hand calculations, intuition, and like what sort of things you should be thinking about when you go from I have all these ideas to how realistic are they?
Awesome.
Yeah. Yeah, and a little bit of background, like the reason I'm focusing mostly on the requirements at this point is because requirements are something that are new to our team this year. And so I want to get as many members of the team as possible fluent in it, fluent in requirements, because it's the foundation of all design everywhere. Cool. So now I'm going to go with a little bit more of a complex example, but also hopefully one that's a little more familiar to you guys. Mark 5. So for our team, essentially, the only technical requirement is that we want to win Formula North. And that is what our car is designed to do. That's what all subsystems should hopefully be building towards. Which is kind of funny if you think about it. Like this is kind of the goal of the entire team. And it's 5 words, including fundamental requirements. It's 2 of them. But what's really important to understand is that like our design does not exist in a vacuum. Like we are at Olin, like we are part of a community. We have obligation to like junior engineer members, faculty, like people that come in and visit Olin. So even though it's like a fairly simple technical goal, that's not actually everything that our team is working for. And so this sort of wraps back into the context thing. Understanding the environment that you're operating in is really important, and also informs your later design decisions. But so now I'm going to talk more about how you actually go from those fundamental requirements down to like the more specific metrics that we were talking about. And the most helpful thing that I've found to think about this is like, what is like asking yourself the question, like, what does that actually mean? And so in this case, like winning Formula North, like, okay, that sounds great. What does that actually entail? What does that actually mean? And for this analysis, I've focused solely on the dynamic events and solely on the drivetrain system, just because that's what I'm most familiar with. And also, frankly, what's the most exciting to talk about in terms of dynamic events, not the components. But so I'm going to be going through one single level that got us down to 2 derived requirements. So essentially, like it went from score well in endurance to having a top 3 lap time, which meant that our car has to be able to go around the track in under 66 seconds, which with some optimum G lap simulation gave us an acceleration number that I definitely did not just guess this afternoon, where we need to accelerate with like this amount of acceleration. That's like, okay, well, how does something achieve that? And that's like with the fundamental equation F equals ma. We can either increase our force or decrease our mass to get higher acceleration. And so then we want to weigh as little as possible, which, as you guys know, is a poor requirement. And what that actually means in this case is that you have a 12 kilogram motor, a 3 kilogram differential, 5 kilograms of structure things that we don't have defined yet, which means that our weight target is about 20 kilograms for this system. And then the output force, we want it to be more than the tires can react. Also, these levels and mass and acceleration. That's why they're not A and B. I realize that could be clear. And so where this number comes from is we did some simple analysis and looked at our specific type of tires and found that the maximum amount of force that one tire could impart was 1,600 newtons under like ideal acceleration case. And so we decided to size our transmission system such that it could apply 3,200 newtons to the road, or greater than 3,200 newtons to the road, meaning that the transmission is not the limiting factor on acceleration, that is tires, which is, as Nate said last week, is the way that things should be designed, such that none of the other subsystems reduce the effectiveness of each other, the vehicle. But what you'll notice is that each of these only represents the first bullet point in this stack up. So inside score well and endurance, you have a top 3 lap time, but you also have finishing endurance. And if this is the accumulator subteam, you'd also have not running out of charge, not overheating, things like that. And so this, you can see how rapidly something as simple as winning Formula North becomes an incredibly large number of metrics that every subsystem on the entire car has to deal with. So like this is a much better illustration of why this is so much engineering work. But it's also really interesting engineering work. And it's worth taking the time to do, because if you poorly define your requirements, you're going to be hammering something with a toothpick, and it's going to be a bad time.
Alex, how would you balance your, like, if you necessarily are trying to output more force, your parts might weigh more, and like how do you strike that balance?
That's a great question. That's not something that I have a definitive answer to, except for the fact that you'd look at acceleration, but you'd also want to look at like the amount of energy that's consumed to accelerate a heavier part. And so if you start limiting other subsystems by being super heavy, that sort of also ties into the way as little as possible.
Yeah, I guess my question was like, why would you do twice the max tire force as opposed to like 1.5 or like 1.1 times the max tire force? You know what I mean?
Gotcha. Sorry. The factor of 2 came from the fact that we have 2 tires, and that's like a per tire maximum force. But that's a good question. This does not have another thing we can talk about later is like factor of safety and margin of safety, which are design tools that you can use to account for uncertainty on your end, but also like poor analysis or like poor, not precise analysis. Did that answer your question? Yeah, I'm looking at it. Okay, so Brent asked, how do you come up with specific numbers? So in this case, these numbers here, like the motor, the differential, the structure, the motor and the differential are known because part of the drivetrain system is that we made the high level decision to reuse components from previous years. So the only part of that that's sort of hand wavy is the 5 kilograms. And that just comes from like experience, like that feels like a right number. As far as the tire force, that also came from a high level suspension choice to use certain racing tires. And then we talked with them, made a simple longitudinal like weight transfer study, to figure out like how much weight would be applied to the rear tires. So like how much force we could expect in the maximum case. And then we multiplied that by 2 to get the 2 rear tires is where that number came from. As far as these upper values, I just looked at the electric vehicles that completed endurance and looked at their lap times. There were only 4 at Formula North last year. So this is really the second to last last place in speed. And then the acceleration number, you should pull that from some sort of lap simulation. I personally just came up with that number because I couldn't find it in our documentation.
I would add to that point that every sub-team can't on their own find the exact final number that it needs. So for example, if you're simulating the car at a high level to inform these numbers for every subsystem, you're going to start with estimates for how much weight you have and what your target weight is. And you're slowly going to refine those numbers as you look into each detailed part and say, here's what we had last year. Here's how much room there is for improvement. If this is our new weight target, here's how the accumulator energy is going to change. If the accumulator energy is changing, now that system's getting lighter. So now our force requirements are different. And you're kind of sifting down iteration by iteration with all the sub-teams together as opposed to each sub-team individually.
Yep.
That's where it's really helpful to have the considerations for each sub-team linked together in some way. So like our lap simulation takes the battery and the drivetrain and the suspension and the tires kind of all into account, and not in a way as detailed as we'd love to have it, but keeping them connected in some way is really important.
Right. And that also limits, like as your systems get larger and more complex, that communication, like your inability to be like perfectly in sync all the time, like limits the performance of that final system. And so like if you're better able to communicate, you're better able to communicate where each team can allow the other to have some leeway, and you'll have more efficient design.
Each sub-team will find the limits of their design. If the tires are one limit for the suspension, then that constrains each additional system. And maybe the motor has a certain amount of force, and that's going to constrain certain parts of different systems. The rules limit how much power you can put out, or the motor will limit how much power you can put out. That's constraining the accumulator, and everything kind of ties into each other that way.
Yeah, you sort of like race car design and like even like every sort of high level system design is always an amount of compromise, an amount of like there are fundamental things like Neil was saying that start to narrow things down, and the reason that our cars look the way that our cars look is opposed to why our cars don't look like F1 cars. Like the fact that we have a rules limited power output has very like large impact on what the design of our car looks like from the beginning. And then the tires that we have access to, like as a racing team, very much change what our suspension geometry looks like. And so it's always a delicate balance of like finding these things and just start to narrow down your system and narrow your system more and more. And like Alex and Neil was saying, like finding the best way as a team to deal with those compromises is like how to have the best race car.
Right. And then there's also some dumb things that inform it, like the fact, like our wheelbase needs to be small enough that we can drive it into the AC. Like that's a driving design consideration that you wouldn't have thought of.
Lightly push it into the AC.
It's a press fit. Like you don't think that the architect that designed the building was a stakeholder in the Mark V suspension.
We literally
geometry.
had to say that in a design review with our alumni and engineers from GM, and they were just like, what constrains your wheelbase or your track? And when they heard that, they're just like, wow.
But something that was really important about that is that you had rationale. Even if they didn't think that it was valid rationale, like you were able to trace like that design decision all the way back to its like fundamental reasoning.
Yeah. And it like sets off our suspension design. Like we start way ahead because we've just made that decision. Or I'm really the decision's been made for us, but like it drives a lot of the design that limited track width.
Right.
And so there are these things that like, I mean, it's all sort of like an optimization problem that's like slowly gets narrowed down until in the end, like all the dominoes kind of have to fall into place, which is like what's like really exciting and like satisfying about the design cycle. But always like if you don't do it well, it's really challenging. So,
Right. Okay. All right, too many more slides. So if you're falling asleep, hang on for another few minutes. So then these are the actual derived requirements that we came up with for the Mark V transmission assembly. And then the idea is that like each of these we came up with from like that fairly arduous process of asking why is this, like how is this true? And then sort of going back to the idea of like all those whack looking lamps from that same requirement. When the subteam gets to the point that their requirements are satisfied, you can begin ideating on like top level system geometry. Something that's interesting to note here, and that is probably a little bit different than the traditional experience, is that when we did these, we were all working together as a sub-team. This wasn't a specific person that owned a specific component doing this analysis. And so like these design requirements are really useful for subsystem level design, but if you try and actually apply them to like singular components, it becomes a little more difficult because their contribution to the overall subsystem's functioning is less clear. But actually, yeah, if you guys have any questions on that, I think that's a big point that I wasn't able to cover effectively in this presentation. But it's just like the idea that designing individual parts is significantly different than doing this sort of like high system design trading. Yeah. And the best I can do is just by saying that each of those small parts need to come together to fulfill the whole requirement for the subsystem. And so like everyone being really well versed in the top level design requirements, at least for their subsystem, is really important. Because then like if you have to present for design, or if a judge walks by in the pit and they're like, oh, like tell me about the scatter shield, or tell me about the brake lever or something, like every single person on the team should be able to be like, okay, well, like we need to cut weight because F equals MA. Like we need to reduce rotational inertia, like all those things that like tie all the way back to the beginning. And that also makes you a kick-ass engineer, because if you understand the system, then you can question like requirements that are put on you. So this sort of represents like the ideation phase for a very small.
Is it just me that lost Alex? Or?
No,
Yeah,
I lost him too.
I cut out. I'm back, I think.
Where did we cut out?
During the ideation slide at the end of it.
This one?
Yeah.
At what point in this one?
When you were finishing up, wrapping up, you were just saying like, oh, this is what we did for ideation.
Okay, cool. Yeah, so then this would represent like that ideation phase. Like there's a lot of pretty like wacky concept represented here, like bending one of the tubes of the chassis, making one of the tubes of the chassis removable, like really sort of stuff that like thinks outside the design box that we've been living in for a while. And then the way that you sort of restrict that like really whack mentality and like the crazy thinking is you do something called the design matrix or a decision matrix. Also not going to get into this super in depth, but you essentially put attributes that are relevant to your requirements, as well as just sort of like general mechanical attributes such as cost, manufacturability, technical risk, things like that. You put those along the top and then weight each of your potential options based on how satisfactory it would be in each of those categories. Multiply the weights represented in this blue row down, and then sum them across. And the one with the highest total score represents like the most favorable design according to the criteria that you put at the top. And so this is the sort of low fidelity analysis that most people expect when you go from ideation to conversion, like converging on a design. And this is like a really strong way to go towards like a single design direction or two design directions from a whole bunch. And also notice this is on Confluence. You should also put them all on Confluence. And then that sort of takes us to the decision point in the design cycle. From that, you would have one idea that you would refine, put in CAD, do a bunch of like ANSYS and all that stuff too, and ultimately be confident that your design is going to be successful because you chose good requirements that were thoroughly thought out and are all justified based on that like fundamental functionality. And I've said this all a couple times, but I'm going to leave this slide up if anyone has questions or comments.
How did you come up with the weight numbers for each of those categories?
That's a great question. Did you guys?
Could you repeat it?
What Keon asked was he was asking how we came up with the weight numbers for each of these categories. Justin and Rachel can speak to this as well. So if you have questions after August 30th, you should ask them. But essentially,
More like May 16th.
I didn't want that felt mean. Essentially, what this does is it's like you go back to your requirements and you look at which of these is most important to the functionality of the team. And so for us, most of it was based on the idea that we needed to have the entire system built, assembled, and in the car by April of this year. All of these other requirements were secondary because if we didn't have it in the car, then we wouldn't get any driver experience. If we didn't have it in the car can't move. There's no way it can win endurance if it doesn't move. And so we sort of prioritized technical risk. Like we prioritized things with lower technical risk because we didn't want any unforeseen challenges to come up and like really damage our timeline. Beyond that, weight was also like one of the bigger factors, as well as cost and install and service. Manufacturability was the least, just because we knew it was a pretty simple system that we could install, like that we could fabricate in a way that was feasible for us as a team.
And if you notice, everything Alex just said was tied to the requirements. So those weights were based off the requirements, which is another really important reason to have your requirements set, because everything can be then based off of your decision making based off of them. Right.
Yeah. It's actually really cool. And it makes you like, engineering is fundamentally like a little scary. If you're like, I do a bunch of math and I build this thing and I expect it to work. And having requirements that like root everything together like this, like lets you sleep much better at night because you like have rationale for every decision that you've made, and know where all your load cases come from and all that stuff. Even if it is a huge amount of work to get all your requirements properly done.
I do want to emphasize that, like, especially like even in the context of not formula, the context is so important in like what you're designing for. And like, for example, in ADE, like we learn about designing for affordability, and like that context is like wildly different because, like, for example, while in here we said we might choose a factor of safety of like 3 because we care about not wanting to break, and that's more important. In other places, in like more rural areas, you would design for a factor of safety of like 1.2 because it's just cheaper, and like cheaper is better. And so like that changes how you design things a lot. And so like looking at your context and understanding that is really important as well.
Yeah, that's a great point. It also sort of ties into the fact that like every single aspect of this has like a massive amount of analysis that could go into every step. Like something as simple as what should our factor of safety be is like there's someone whose entire job at SpaceX is to determine what the factor of safety should be for like every conceivable combination of use case, material, analysis level, everything. And so I think one of the most important things you can do as an engineer is acknowledge that there's a lot of things that you're not thinking about in any decision you make, and like just live with that awareness so that you never get caught off guard by like, oh, like I just assumed this would be okay. Like always assume it's not okay. But if you have reason to believe it'll work, then it'll probably work.
Can I get a quick one?
Oh yeah, of course.
I just think it's important to like note that even though like a lot of stuff is talking about broader like subsystem level requirements, I think it's like absolutely essential that every single team member understands those requirements and understands like why we have them and where they come from, because like not only will the parts that you design be better because you have a sense of the context of like why the brake pedal needs to be like a certain amount of weight or why it needs to have a certain amount of travel or anything like that. Like having an understanding of the entire context of the vehicle will just make you a better engineer overall. And like when you can think and talk about things and like subsystem levels and understand like all the complex relationships and like system level relationships between everything, like you will just understand fundamentally why so many decisions get made on the car. And when you can do that, you can approach like this is like Alex's whole point. Like when you can do that effectively, you can approach any system. And like when you can like fundamentally break down those system level relationships, you can just get so far and do so much. And so it's like essential for like, you know, even like, you know, incoming junior engineers, people who like feel like they don't really understand engineering or like haven't learned anything yet. Like even if you're just designing one small part on the car, like knowing this stuff makes a big difference.
Right. And it's way more fun.
Definitely.
Because like if your boss just hands you a list of things you need to do, that sucks. But if you understand like why, way more fun. Also, if you guys are curious, this is what the actual requirement document for drivetrain looked like this year. Notice that like the technical part only comprises like just under half, and there's a lot of onboarding financial documentation goals that are also attempting to be as number oriented and metric driven as possible, but with mixed success, I would say, on our sub team. Yeah, the comic ended up not being relevant, but I thought I would throw it in here anyway because I liked it.
Do you think that if you design for all of your requirements, you will be successful? Is that an absolute?
It depends on how well you've set your requirements, I think, is the answer to that. So it's sort of like the idea that like your requirements state the characteristics that your design must meet in order to be successful. And so if you define your requirements such that, like imagine you're just sitting in a room with a whiteboard, like you've done no building, you've done no analysis, you just think like, what does my ideal formula car look like? And you can like come up with a really long list. And if you design such that you hit every single item on that list, then it will be a really successful functional system. The difficulty comes in picking the correct requirements because like if you have holes in your knowledge, that becomes really difficult. And then actually like effectively executing on all of them. Because like, as you know, like the more things you have to do, like the more balls you have in the air at the same time, the harder it is to focus on any one of them. And the more likely it is that like some small issue falls through the cracks.
I would add that, or I would think of it kind of that if you design something that hits all your requirements, you created a design that has the ability to be successful at its baseline. Because in the end, if you build the perfect formula car and your driver sucks, then that person took a design that should be successful or could be successful because the requirements in the design say it could be, but still isn't possible or still doesn't achieve the right thing. And I think it's important not to conflate lack of success with lack of a well done design. And I think that applies to everything. Like your requirements should also dictate the game plan for your company, for our team. And if that shows us, oh, we need to train our drivers, or we need to build this factory, we need to do this, like the process kind of also is dictated by your requirements, and those need to go in hand for the design to reach its potential and how it's used.
Right. And I also feel like it's easy to look at this and be like, okay, well, every year we want to win. So like, why does the system change from year to year? Mm-hmm. And so like something that's really important is that you continually reevaluate your requirements to make sure that your assumptions are correct. So like this year we added a bunch of requirements after that we made this document about like redundancy of chain tensioning because our chain broke every single time we tried to drive the car. So like as you get new data, update your requirements.
And for us, it's also important that the context is always changing. the teams around us are also getting better, and the benchmarks for what success means is constantly increasing. Our budget is constantly changing. The people on our team is constantly changing. The resources we have is constantly changing. So every year, the threshold for what winning Formula North can be is very different every year.
Also, for context, this is the first year that this has been our goal. Like, it has never been explicitly stated in this way, and at least the like vibe on the team has not been that this was explicitly our goal. It was like to finish certain things, to make sure that we have a car built by Formula North, right? Like,
Right.
that's why it's really important to be thinking about these things as early as possible, because it changes not only what you do on your team, but also every single person like thinks about coming and working on the team too.
Yeah, that's really important. Like winning Formula North is not the peak of where our team can go still. There's still bigger competitions out there, and we've come so far to get to this point, and there's still so much more for our ceiling to reach.
Win F1.
Yeah, we should be beating the Mercedes team.
Louis Hamilton.
Louis Hamilton.
Oh my god. Also, fun fact, the term formula comes from the fact that like the rules are so restrictive that it's like a formula, and like the car is always going to look the same. Like the car from all the teams are always going to look the
Really?
same. Yeah.
Wow, that's great.
Which is kind of wacky. It kind of undercuts the like design convergence metaphor, but yeah, I'm gonna go.
I mean, even in that vein, I think it becomes a lot less scary to think of how many decisions you have to make when you remember how much the context around you and the rules of the competition make so many decisions for you already. Just the fact that we have a certain budget, certain tools in the machine shop, and certain times we can access them can constrain our design by like, let's say 90%. And that makes it way less scary to have to choose between an infinite number of options versus a finite number of options. And the rules are a huge place for that. And the team kind of has many ways of thinking about that and make it a lot easier.
And for the specific transmission design, they took all of their requirements, but they had to fit within the box that chassis gave them, right? So like, there is these things where it's like you, you have like all of these requirements which can guide you, but you'll also have like limits, and this is what Nate was talking about earlier, but like you'll have limits from every other team too.
Yep, especially that suspension team.
I'd like to say that that's a good example of a breakdown of like not and like had we been more considerate of that and like understood transmissions goals as well as suspensions goals, we would have avoided that problem.
Yeah, had transmission had the time to do work over the summer, it would have been possible.
Right.
Nice. A little early even.
Requirements are important.